Hello, my name is Peter Shea, and I am a researcher at the National Energy Technology Laboratory. Today, I would like to share with you my work on the deformation of pyrometric cones and coash cones at high temperatures. I am grateful to Material Science and Technology 2020 and the session organizers for the opportunity to do so under such extraordinary circumstances. Thank you. The principle of consilience states that evidence from different fields of study should not be contradictory. Moreover, the convergence of evidence from different approaches strengthens the conclusions that may be drawn. Such is the case for material science and earth and planetary science, particularly for ceramic engineering. Direct analogs for ceramic fabrication processes may be found out in the natural world. Conversely, engineered products may be viewed as a special case of pyrometamorphism. Many important industrial processes begin with minerals that are subsequently transformed by exposure to high temperatures. A good example of this is the production of traditional pottery, ranging from earthenware to stoneware to porcelain, where the maturation of the body and glaze proceeds through high temperature physical and chemical changes that transform the minerals into the final product. Likewise, the same high temperature processes act on sedimentary minerals present in coal and transform them into ash and slag. Our ability to predict the effective viscosity of a molten silicate and the propensity for liquid phase sintering can provide useful insights into clinker formation and slagging for industrial boilers and coal-fired power plants. Volcanologists often employ the Einstein-Roscoe equation to help explain the effective viscosity of subliquidous magmas that contain one or more solid phases in suspension. The presence of the solid phase leads to an increase in the effective viscosity of the magma relative to its intrinsic viscosity. Using CalFAT thermophysical modeling software, it is possible to predict the solid phase volume fraction present in a two-phase system given the major oxide composition, temperature, and oxygen activity. The intrinsic viscosity may then be estimated using the modified quasi-chemical model based on the composition of the molten phase, also from thermophysical modeling, and the temperature. This approach to modeling the effective viscosity of subliquidous molten silicates helps to answer a very old question in ceramic engineering. How do pyrometric cones actually work? The modern pyrometric cone was invented by Seeger at the Royal Porcelain Works in Berlin, and the first written account was published in 1886. The pyrometric cone was subsequently introduced to the United States by Orton, and the first thermophysical description for pyrometric cone deformation was published by Sossman in 1913. Sossman hypothesized that pyrometric cones start to deform at or near the eutectic temperature of the mineral mix used in their fabrication, and that the viscous nature of the molten oxide slows the cone collapse under its own weight. If Sossman is right, then pyrometric cones work by integrating viscoplastic strain over time, where the effective viscosity is controlled by the cone compositions developed by Seeger through empirical experimentation. In 1968, Thomson published a doctoral dissertation on the thermal deformation of glass crystal systems while a student at The Ohio State University. Thompson was concurrently a research engineer at the Wharton Ceramic Foundation and wished to measure the effective viscosity of pyrometric cones at high temperatures. He did so by constructing a 3-point beam-bending viscometer, with which he measured the effective viscosity of cones 4, 5, and 6 as a function of temperature. What Thompson lacked at the time was access to thermophysical modeling software capable of computing the effective viscosity of these pyrometric cone compositions in a subliquidus state. Subsequent advances in computers made it possible to apply thermophysical modeling to a wide range of problems, including the estimation of effective viscosity for subliquidus silicate melts. The effective viscosity estimates found through thermophysical modeling were in excellent agreement with Thompson's experimentally measured viscosity values, lending support to the validity of the approach. If accumulation of viscoplastic strain due to gravity is the answer, then a pyrometric cone held at a constant temperature greater than its solidus temperature should also reach its endpoint through bending given sufficient time. This appears to be the case based on data from Vukovic and Frank as well as Bunzel. The next question is, can thermophysical modeling predict the endpoint temperature of a pyrometric cone given just its major oxide composition? The answer, surprisingly, appears to be yes. A positive linear correlation was found between the Lyttleton softening point temperature, or the temperature at which the effective viscosity is 10 to a 7.6 poise, and the pyrometric cone endpoint temperature. The choice of the Lyttleton softening point is not arbitrary, as it is typically considered to be the start of the working range for glass. It is one thing to predict the effective viscosity of pyrometric cones, which are formulated with a handful of carefully selected minerals and prepared in large batches with consistency as a key performance objective. How well does the thermophysical modeling approach work with the Coash fusibility test, which must contend with a much wider range of mineral compositions? The Coash fusibility test, or AFT, was inspired by pyrometric cones as a way of measuring the propensity for coal ash clinkering. The AFT critical temperatures figure prominently in the assessment of coal quality even today. The U.S. Geological Survey's coal quality database contains many records of coal ash composition and AFT critical temperature that can help provide an answer. 4726 records, which contain major oxide data and at least 2 AFT critical temperatures, were selected and analyzed through thermophysical modeling. The results suggest that a major re-evaluation of how coal ash AFT critical temperatures are used is in order. This is because these critical temperatures measure heat work, or the combined effect of time and temperature, in the same manner as pyrometric cones. Contrary to expectation, AFT critical temperatures are not strongly correlated with the solidus temperature, but are correlated with the liquidus temperature. So what is going on here? A possible answer is that the Lyttleton softening point temperature of a coal ash mixture is just below its liquidus temperature, as suggested by prior work on pyrometric cones. There is some evidence of this when one considers the predicted effective viscosity of coal ash slags at their AFT critical temperatures. The effective viscosity of most coash cones lie within or below the working range of glass once initial deformation begins. Therefore, much as was the case for pyrometric cones, the deformation of coash cones during fusibility testing is the accumulation of viscoplastic deformation due to gravity and surface tension over time. Interestingly, the temperature distribution at the Lyttleton softening point correctly reproduces the bimodal distribution observed in the initial deformation temperature from the CoQoL database. This is probably not a coincidence. But, to be sure, the modeling approach was checked in the lab through high-temperature rotary viscometry with two synthetic coash slags, a high iron slag and a high silica and alumina slag. The same slags were also subjected to AFT measurements. The results for the reducing atmosphere case are shown in these two plots. Since no significant difference in AFT results was observed for the high silica and alumina sample, only data on the high iron sample will be shown on the next slide. Rotary viscometry of the high iron slag was repeated using a carbon dioxide atmosphere and again in air. An increase in viscosity of 1238 and 1285 degrees C were observed under inert and oxidizing conditions, respectively. The softening temperature and hemispherical temperature were also significantly higher for the high iron slag, which means that the slag is much less viscous and less prone to undergo viscoplastic deformation at lower temperatures compared with the same slag under reducing conditions. This is consistent with the non-bridging oxygen per tetrahedron model of silicate melts that is often encountered in both materials engineering as well as earth and planetary science. Iron oxide exists in both a divalent and a trivalent state, while iron 2 oxide acts as a network modifier and reduces the viscosity of a silicate melt by increasing the number of non-bridging oxygens. Iron 3 oxide acts as a network former. Consequently, oxygen activity plays an important role in determining the effect of iron oxide on coash slag viscosity. However, that's not all that can be said about iron oxide. Researchers in earth and planetary science have reported a miscibility gap in the molten silicate system where silicon-rich and iron-rich phases separate. To account for this liquid-liquid immiscibility, the thermophysical modeling in this study was done with a two-phase slag instead of treating the molten phase as being uniform in composition. The modeling results suggest that a phase inversion between the silicon-rich and iron-rich phases may lead to an abrupt discontinuity in the effective viscosity of the molten silicate phase above the liquidus temperature, where no solids are present, while phase inversion has been observed for oil and water emulsions and water and oil emulsions. The discontinuity in viscosity as a function of temperature has not been verified for molten silicates in the lab, at least not yet. To summarize, pyrometamorphism in petrology is consilient with pyroplastic deformation in ceramic engineering and coash fusibility testing. Next, thermophysical modeling is useful in predicting the effective viscosity of partially molten silicates. Lastly, iron oxides play an important role in determining the effective viscosity of molten silicates, not only through its role as a network former or modifier, but also due to immiscibility and liquid-liquid phase separation. For more details, particularly on materials and methods, please check out my papers on this topic. I won't ask you to like and subscribe, but if you find the data, modeling approach, or the literature review to be useful in your work, a citation in your next paper would be much, much appreciated. Lastly, and most importantly, the standard disclaimer of liability or endorsement for the U.S. government applies. My email address is peter.shea@netl.doe.gov if you would like help with a Python script for FactSage data entry and analysis. Thank you very much for your time and attention.